Okay, let's have the extended real number. This is the set of extended real number, which is the union of the set of real numbers and the set with elements negative infinity and positive infinity. Now we have here some properties of extended real number. If we have here a real number x, then we have the sum of a real number and the positive infinity is equal to positive infinity. Then x minus infinity is negative infinity. So the product of a real number and the positive infinity is positive if x is positive, and it is negative if x is negative. Here, the product of a real number and a negative infinity is positive when x is negative, and negative infinity when x is positive. Also, we have here the sum is equal to positive infinity. Then we have negative infinity minus infinity is equal to negative infinity. Then positive infinity times positive infinity is positive infinity, while infinity times negative infinity is equal to negative infinity. So here, negative infinity times positive infinity is negative infinity, while negative infinity times negative infinity is positive infinity. So we note that this is left undefined, and by convention, we can say that 0 times infinity is equal to 0. Now let's have here the remark. For any non-empty subset S of a real number R, set of real number R, and S has no upper bound, so it means S is not bounded above, then we write that the supremum of S is positive infinity. Now here, with respect to the extended real number, the supremum of empty is negative infinity. Why? With respect to the extended real number, whereas with respect to the real number, the supremum of infinity does not exist. Here, the supremum is negative infinity. Now take note that infinity is a subset of any set. Therefore, every extended real number is an upper bound of empty. That is, the upper bound of this set here, upper bound of empty, is the set of extended real number, that is R, union this set, and of course this is equal to closed interval where negative infinity and positive infinity are included. So when we talk about the supremum of empty, we know that the supremum is the least among all the upper bounds of the set. So because the upper bounds of the empty set is this one, and the least element is negative infinity, therefore the supremum of empty is negative infinity. Okay. Next, we have here, again with respect to R star, the supremum of S exists for all subset S of the set of the real number. Because if there is no upper bound of the set S, we say that the supremum of S is positive infinity. And take note, in the extended real number, the positive infinity belongs to the set of the extended real number. Next is, if the set S is not empty and it has no lower bound, then we can say that the infimum of this set is the negative infinity. So again, with respect to R star, the infimum always exists. Number 5, we have here the infimum of empty is equal to positive infinity. So kindly explain this one as your problem set number 3. Why is that the infimum of empty is positive infinity? So here, the infimum of the set S, where S is a subset of the set of real number, exists. It may be positive infinity or negative infinity. Okay, for the completeness axiom, with respect to the set of real number, every non-empty subset of R that is bounded above has an upper bound. It has a supremum. So, actually this statement is not proven, but then it is generally accepted. And then we have here the dual of the completeness axiom, which states that every non-empty subset of R that is bounded below has a lower bound, has an infimum. So if it is bounded below, it means it has a lower bound. Therefore, that set has an infimum. So for the proof of that, we will let A be any non-empty subset of R that is bounded below. So, since it is bounded below, then A has a lower bound. So, just like here, let's try to consider set A. So for set A, we have here set of real number line. So for example, this is A, and if A is bounded below, it means it has a lower bound. So this would be the lower bounds of A. So say for example, we have the element or a real number C, which is a lower bound for the set A. By the preceding theorem, in our preceding theorem, it states there that if C is a lower bound for A, the negative C is an upper bound for negative A. Hence, negative A is a non-empty set that is bounded above. So, it is bounded above. Okay, so let's extend this one. Okay, for example, we have here 0. So negative A is here. This is negative A. Okay. So negative A. Of course, this is our negative C. So as you can see, C is a lower bound for the set A, and negative C is an upper bound for this set negative A. So, according to the completeness axiom here, according to this statement, that every non-empty subset of R that is bounded above, because the set negative A has an upper bound, so it means this negative A is bounded above. So since this is bounded above, negative A rather, has a supremum. Let's have this. Okay, by the completeness axiom, it means the supremum of negative A exists. It means it has a supremum. Now, by the preceding theorem, it means that the infimum of A exists. And we're done. So that's what we are looking, the supremum of A, the existence of the supremum of the set A. So that's the end of the proof. Let's have Theorem 2.2. Let a non-empty subset A of the set of real number and a real number alpha. First, alpha is the supremum of A if and only if the intersection of this interval and A is empty, and the intersection of this interval and A is not empty for any epsilon greater than 0. Now, to illustrate that one, let me have this, the real number line. Okay, say we have here set A. This is set A. And then, this is our alpha, which is equal to the supremum of A. So, if we take an open interval from alpha to positive infinity, say we have alpha to positive infinity, and then if we are to take the intersection of A to this set, it is empty. It means there is no common element. Say, if we are to close this interval, it means alpha is, the supremum of A is in A. Still, if you get the intersection of this set here, set A, and this open interval, the intersection is empty. There is no element in common. Also, for any epsilon greater than 0, say we have here alpha minus epsilon, and this is alpha rather. So this set here can be written as open alpha minus epsilon to alpha closed. And if we are to get the intersection of this set and A, there is a common element, or the intersection is not empty. Why? Because as you can see in our illustration here, this is the set A here, and this is the smaller set alpha minus epsilon to alpha. So as you can see, there is element in common, or there could be elements in common. Say we have an element A. Therefore, the intersection is not empty. And then for the next statement, we have alpha is the infimum of A if and only if the intersection of this interval and A is empty, and the intersection of this interval and A is not empty for any epsilon greater than 0. So the explanation is most likely the same for the second statement. And let me have this one. So consider again this. Okay, so for example, we have here our set A, then this is alpha, which is equal to the infimum of A, and this set here, open set, there is this set, this interval, and if we are going to get the intersection to A, of course it is empty, or there is no common element. Whereas for any epsilon greater than 0, if this is alpha plus epsilon. Distance from alpha to this is epsilon, so this is alpha plus epsilon. Now if we are to take the intersection of this interval here from alpha or closed alpha to epsilon, alpha plus epsilon, okay, the intersection of this to the set A is not empty. So it means there is, or there are common elements here. Here, this set to set A. Okay, let's now prove the first statement. Take note, we do have if and only if statement. So we will prove necessary and sufficient conditions. So let's have first the necessary. It means if alpha is equal to if alpha is the supremum of A, then we will show that the intersection of this is empty and semi. So we will show that one. So suppose this is our assumption. We have alpha is the supremum of A. So by the definition of the supremum of A, alpha is greater than any element of A. So element of the set. If we have this, 1. So of course we have, if this is set A here, so alpha is here, which is the supremum of A. Of course, the elements here, A, in A, all the elements here, because this is the supremum, we have A is less than or equal to alpha for all A in A. So alpha is greater than or equal to any element of A. That is, A thou is a subset of this open interval. Now, as you can see, that open interval, not siya, from from alpha to this is our open interval. This is the one. Yeah. This one we have from negative infinity to alpha. We have this. As you can see, A is contained in this interval. So we have A is a subset of A. So A is just a smaller set. So let's have it here. So in this interval, this is the bigger set than this set. So this is set A. it is contained or a subset of the bigger interval, this one. This implies that if we are to take the intersection of, because this is a subset, A is a subset of this one, if we are to take the intersection of A to positive infinity, so A intersection A, or alpha rather, alpha positive infinity, it is empty. Next, by the way, we have shown this, and then for the next, for any epsilon greater than 0, so we let epsilon greater than 0, then, of course, since this is greater than 0, if we are going to subtract it from alpha, this is less than alpha. Since alpha is the least upper bound, so take note, for the least upper bound, it is the smallest among all the upper bounds. So if we have this, alpha is the least upper bound, and if we have here alpha minus epsilon, the least upper bound, this is the smallest among all the upper bounds, the upper bounds of A, the smallest among all the upper bounds. It means, ang mga upper bounds, mag-start siya sa alpha to the right. Therefore, this one is not anymore not an upper bound for A. So, we have this one. This implies that if this is not an upper bound, this implies that there exists A in A such that A is greater than alpha minus epsilon, or alpha minus epsilon is less than A, as you can see in the illustration. Since alpha is an upper bound for A, this alpha here is an upper bound for A, so it means, kung upper bound siya for A, it means alpha is less than or equal to, alpha, A is less than or equal to alpha. And we have shown a while ago that this is true. Okay, so we have this one. Thus, we have this one. Thus, this element here, A, is in the intersection. So as you can see, there is an element A here in between this smaller set. So if we are to get the intersection of this set, bigger set, and the smaller set where A is here, the intersection is not empty, wherein there is an element A. So we're done proving the necessary. Okay, for the continuation of the proof, please watch the next video. Okay, for the continuation of the proof for Theorem 2.2, we have this one. Let us have a recall. This is the statement that we're going to prove. We're done the necessary statement. So we will prove the other way. It means we will assume that this is true, and then we will show that alpha is the supremum of A. So let's do this. So suppose we have this statement. The statement is true. Then we want to show that alpha is the supremum of A. Since, of course, by our assumption that the intersection of the two sets here is empty, therefore, it follows that A is contained in the complement. Now, to show that one, let's have this. So say we have here set A, then say this is alpha, and then based in our assumption, A intersection alpha to positive infinity is empty. Now, if we are to get the complement of this, alpha, the complement of this is eta. So as you can see, the complement of this interval is bigger than set A. So it means A is contained in the complement of the interval. Note that this is, of course, equal to this set. This implies that A is less than or equal to alpha for all A in A. Because we have here our alpha. This is our alpha here. So since A is contained in the complement, so we can say that A, all the elements here, is less than or equal to alpha for all A in the set A. This shows that alpha is an upper bound for A. So because we have here our definition for an upper bound, that if A is less than or equal to alpha for all elements in the set A, then this is the upper bound for A. Now suppose alpha is not the least upper bound for A. So we are to suppose that alpha is not the supremum of A. So we will be using here contradiction. Then, since it is not the alpha is not the least upper bound, and we know that alpha is an upper bound, right? Here in this statement, alpha is an upper bound, but it is not the least. We assume that it is not the least. So the supremum of A is less than alpha, because we know the supremum of A is the smallest upper bound, where alpha is an upper bound. That is, from this inequality, we can rewrite that as this: A minus the supremum of A is greater than alpha, because this is greater, so minus the smaller is greater than 0. So since this is greater than 0, we can let this as our epsilon, which is alpha minus the supremum of A. Then by our assumption, we have this one, ito, alpha minus, so we just substitute epsilon by alpha minus epsilon. So we have alpha minus supremum of A, then we have up to alpha close interval intersection A. Okay, so this is equal to, this is na 0 siya, then positive supremum of A. So this is equal to this interval, supremum of A, alpha, mani siya, kani. Then intersection ni A is not empty by this assumption. It's not empty. So, since it is not empty, we can let any element. So, A is in this intersection, okay, not empty man. Then, the supremum of A is less than A. Why? Okay, let us have this illustration. So, since A is contained in the supremum of A, from supremum of A to alpha, let's see that ito, intersection A. So it means we have this illustration. So supremum of A is here, alpha is here. So we have here set A, and as you can see, there is an element in common to this set and with A. So say for example, A is here, element A is here. So in that case, we can say that the supremum of A is less than 8. So we have this one. This is a contradiction. Contradiction to the fact that the supremum of A is an upper bound for A. Because we all know that the fact is A should be less than or equal to the supremum of A, being the supremum as the least upper bound of A. So this is the fact, and then we have come up to this. So we have a contradiction to the statement. Since we're using proof by contradiction, we suppose that A is not the least upper bound, and we have found a contradiction. So we can conclude that A is the least upper bound, or A is the supremum of, or alpha rather, alpha is the least upper bound, or alpha is the supremum of A. So we're done proving the first statement, the if and only if statement. So for letter B, this will be your problem set number 4. Now let's have the Archimedean principle, or AP. So we have here, so if x is a real number, then there exists a natural number n such that x is smaller than that natural number, or it could be equal. So just like for example, if x is equal to 2.5, so there exists a natural number, say 3, say 4, say 5, which is greater than the real number, or x is less than the natural number. So let us have a proof of this. We let a real number x, and then we will consider the following cases. First case, if x is negative. So if x is negative, of course we can take n equals 1, wherein a negative number is less than 1. Next case, if x is equal to 0 or positive, so we will let the set k in the natural number union 0, or k is a whole number such that x is less than or equal, k rather is less than or equal to x. Then of course 0 is in the set S, so k could be 0 because k is a whole number. Hence, so if k is 0, k is 0, 0 less than or equal to x is 0 or positive. So 0 is in S, since S is not empty. Clearly, x is an upper bound for S. So X is an upper bound for X. Okay, we have here the set S na condition na all the elements here in K such that less than or equal to X. So clearly X is an upper bound for S. By the completeness axiom, of course, S has a supremum. If the set has an upper bound, it has a supremum. So say Y. It follows that there exists K in S, K in the set, such that Y minus 1/2 is less than K. So we call this by Supremum property theorem. So actually we have proved this one. Let me have recall about the Supremum property theorem. Okay, this is the Supremum property theorem. That if U is a supremum of S, then for any epsilon greater than 0, there exists S in the set such that this is satisfied. So in our proof, we have Y as the supremum. Yes. The supremum of we have here Y is equal to the supremum of the set S, and then it states there in the Supremum property theorem that there exists K in S such that Y minus 1/2 is less than K. So actually, our 1/2 here is the epsilon. So Y being here, Y being the supremum of S here, and then there exists K in S such that Y minus 1/2 is less than K. So epsilon is 1/2. Okay, that's for the Supremum property theorem. Okay, from this one, we have Y minus 1/2 is less than K. So we just add 1 to both sides. So we could have Y minus 1, I plus 1/2 less than K plus 1. And we all know that Y plus 1/2 is greater than Y. Or we have this one, hence K plus 1 is greater than Y plus 1/2, which is greater than Y. This implies that K plus 1 is not in S. Why? Okay, this is because our S here is the set the set of all K such that K is less than or equal to X. And then, if K plus 1 is in S, we should have this. K plus 1 is less than or equal to Y. But in our result, there, K plus 1 is greater than Y. Here, K plus 1 is greater than Y. So we can say that K plus 1 is not in S. Therefore, since it is not in S, K plus 1 is greater than X. So we set N be equal to K plus 1, then N is in N, and moreover, X is less than N. So we set this one as N. So we're done. We have shown that X is less. Okay, let's have corollary 2.1. Let A and B be real numbers with a greater than 0. Then, first, there exists a natural number n such that a times n is greater than b. There exists a natural number n such that 1 over n is between 0 and a. Then, next, there exists a natural number n such that a is greater than or equal to n minus 1 but less than n. Now, to prove the first statement, we are to find the existence of a natural number n such that a times n is greater than b. With this condition, where a and b are real numbers and a is greater than 0. So we have this. Since a is greater than 0, from our assumption, we could have b over a. b is a real number, a is a real number greater than 0 or not equal to 0, therefore x is a real number. Now, by Archimedean principle, the Archimedean principle, it states there that if x is a real number, then there exists a natural number n such that x is smaller than n. So that's why we have here, this is x, b over a, less than n. Hence, we have a times n is greater than b. So, we're done proving letter A. Now, let's have letter B. We let x be equal to 1 over a. Take note, a is greater than 0. Therefore, x is a real number. Hence, the Archimedean principle again, since x is a real number, then there exists a natural number n such that this x here, 1 over a, is less than n. That is, 1 over n is less than a. So, because 1 over n is greater than 0, so we have this. So we're done proving letter B.